Paola Passalacqua, and with a joint presentation also from Patrick Bixler. They're from the Texas University, and their presentation is about integration of flood inundation and socio-demographic vulnerability in a techno-social approach for quantifying household flood risk.
That's a long title. Thanks, Albert. Actually, we were just discussing offline that this is a perfect segue to the presentation before, and you'll see why. There's actually a lot of collaborations between the UT Flood Group and the National Water Center. So I'll let Patrick start, and then we'll switch halfway through. Patrick.
Yeah, hi everyone. Thanks for having us. It's great to be part of this forum. Just a quick background. So we're going to be presenting some joint work that Paola and I have been working on. I'm a sociologist by training, but I think maybe an engineer at heart. And Paola is an engineer by training, but maybe a social scientist by heart. She sure generates lots of good theories and hypotheses around how the social interact with the flood mapping that was just presented. In a lot of ways, we're using a similar or the same kind of technique to look at the intersection of population sensitivity, adaptive capacity, and flood hazard exposure. Next slide, please. So Paola and I have been working together. We sort of first met at a dissertation committee, and we originally, or very quickly identified this overlapping interest we both have in network science. And so that kind of brought us together talking. And since then, we've been part of a Bridging Barriers initiative through the University of Texas called Planet Texas 2050. And really sort of our vision or our tagline is to transform the science and practice of hazard preparedness and response with a network approach. We have two objectives: to conduct rigorous research involving network-based approaches to integrate social information, inundation information, governance, and transportation models. So we're trying to generate different types of layers, frequently using a network approach, and trying to understand how those layers interact over space. And then we really sort of have this bigger goal too, to increase the depth and breadth of integration of knowledge across multiple natural hazards in Texas through a co-production approach with academics and non-academic stakeholders. You can tell probably who wrote the first one and who wrote the second one. But this sort of co-production approach, we're really working on the ground with stakeholders, trying to generate knowledge and information that's useful to them. You know, I think as this has sort of unfolded, it's really posed this question to us: how do we understand and build urban community resilience? What is urban resilience? What is community resilience? Really loaded sort of words. But how do we think about this urban community resilience to climate-driven hazards? And obviously thinking about urban flooding issues, whether it's coastal and sort of cyclone, hurricane driven, or largely pluvial in central Texas and urban environments. We really sort of are trying to unpack what makes communities resilient, what makes communities vulnerable to the impact of flooding. Next slide, please. And so it's sort of led us to think about how do we integrate social, ecological, hydrological, and technical information. And that kind of gets us to these multiple layers of transportation, I see in the comment, levees, built environment variables, hydrological, ecological variables, and then the social variables. And I think part of the challenge here is this is really a multi-level issue. And the way we model exposure, the way we model sensitivity, the way we model adaptive capacity, sort of can and should be done, and theoretically is proposed and empirically is done, sort of at household levels and neighborhood levels and across metropolitan scales. But we have a good framework come sort of out of the climate adaptation literature. There is this framework of vulnerability. I know different disciplines, it's been really interesting working together and sort of submitting papers together in these different venues, because different disciplines frame vulnerability and how we think about this formula, how we think about risk, what's the formula for risk, in slightly different ways. But we feel we have a pretty good formula here with vulnerability as it comes out of the climate adaptation literature, which really looks at exposure, sensitivity, and adaptive capacity. Next slide, please. We see a lot of work. There's a lot of work in the hazards and the risk reduction, hazard science and risk reduction literature that are taking up this social vulnerability approach. And so we largely see this as a way to frame susceptibility or sensitivity to the impact. Frequently, when you read about social vulnerability, it talks about sensitivity and adaptive capacity. I think my personal and sort of, I guess, professional opinion is that social vulnerability indices lack the ability to speak to some dimensions of adaptive capacity. But in terms of providing a good indicator of being sensitive to the impact of a potential hazard, it's a pretty good representation. But that sort of leads us to this issue of scale. In order to develop social vulnerability indices like they have been done, at least mostly in the United States. So the Centers for Disease Control has a really good one. Out of the University of South Carolina, Susan Cutter has one, the SOVI, I guess they're both SOVI indexes, but they use census data, and census data, sort of the lowest level of resolution for census data is around the census block group, somewhat related to a neighborhood. But they're this combination of variables. And so what we did in Texas is start with the Susan Cutter et al. Sort of model, which originally, or I guess her model includes 29 variables across the United States. We started with those 29 variables and we made a social vulnerability index using a similar approach that includes a principal component analysis, but that was unique to Texas. And through the combination of data availability and the principal component analysis, we ended up with 19 variables along the categories of, or the components of wealth, language and education, age related, so young, children and elderly, housing status, social status, and gender. And so then we're able to take this information and map it spatially, again, by those census block groups. And this is what that social vulnerability index looks like in the city of Austin. Just kind of a real interesting side note is clearly there's a big distinction. City of Austin has a historical legacy of racial segregation, which sort of has translated into contemporary economic segregation between the east and the west side of Austin. Next slide, please. And so we sort of, so if we're thinking about the sensitivity, we've also been doing some work thinking about the adaptive capacity. One of my areas of research interest is social capital. And so I think if we think about adaptive capacity, it has a number of dimensions, sort of human capital, financial capital, but I also think social capital is a really important piece of that. The ability for households, for people, for communities to be able to adapt when exposed to a hazard or a flood event. And so we did some survey research here in Austin where we measured social capital and looked at how it relates to flood risk perception and flood mitigation behaviors. And so sort of in this model, it was recently published in Frontiers in Water, we demonstrate this effect, this positive effect that this social capital, I think really what we were measuring, and we talk about this in the article, is a measure of bonding social capital, kind of neighborhood cohesion, trust networks, but able to demonstrate the positive effect that social capital has on residents taking these flood mitigation behaviors, even when controlling for social vulnerability. So I think that there's this element of sensitivity, but when controlling for that sensitivity, we can still demonstrate this effect of kind of adaptive capacity, or at least the social dimensions of adaptive capacity. Next slide, please. And so that kind of leads us into thinking about how does all this fit together into a model, the ability to model community resilience. If we can think about these different metrics and measures of adaptive capacity, albeit at the household scale, we can measure and sort of think about sensitivity, but at the census block group scale, how do we then take some of these new techniques and sort of advanced techniques for modeling to think about the right size and the right scale for flood exposure modeling. And at that, I'm going to pass it over to Paola.
All right, thanks, Patrick. Yeah, so we wanted to show you then an example of how we are integrated this information with the flood inundation. So as Patrick said, we are looking at a variety of hazards, but because of our background and my background, we're starting with flooding as the primary application, let's say, for this project. And so when you start thinking, this is why I was saying that this is a perfect segue with the previous presentation, because actually Mark and Derek made my life extremely easy because we're using very similar tools to the ones they just presented. So when you think about flood inundation mapping, there's various, let's say, ingredients that need to go into a flood inundation map, right? So you need a way to forecast flows. you need some terrain information, you need some information where the rivers are, and of course, you need a mapping approach to create the flood inundation map. And let's say there's a variety of methods, there's a variety of resolutions, there's a variety of ways in which you can do this of various complexity. And I would say no method is perfect, and often the solutions really come from looking at a hierarchy of methods, at a hierarchy of approaches that can be integrated together. So the one that we have chosen, and really the one that we wanted to develop, was a simple and fast approach that would be developed with the emergency responders to essentially provide information for emergency response. And so you see here, essentially what Mark and Derek were showing is a national water model, which we're using. In fact, there's a lot of collaborations between David Maidman, Harry Havens, and other people in our group with the National Water Center. And in fact, this project, actually, this part of the project that I'm showing you was in fact funded by NOAA under the JTTI program. And essentially what we looked at is if I go from 10 meter, which is what Mark and Derek were showing, to a 1 meter resolution, what adjustments do I have to make to the same approach? The first thing that you start noticing is that when you start looking at the NHD lines and you place them on LiDAR, this is a hill shade of LiDAR data, you start seeing that the flow line, in fact, is not super accurate, right? Because it wasn't traced a LiDAR resolution of 1 meter resolution. And so what this project looked at is then how do we improve this flow line, still keeping the same density, right? Eventually the national water model will run over higher resolution networks, and so we'll have a higher density network. But as of now, that's a network is being routed on. So how do we take that network then, keep the same density, but improve the accuracy of the center line so that it follows the terrain information? So we're using this approach, which became, GeoFlood, as developed under this NOAA JTTI funding and Planet Access 2015. And so what we do is that we take the endpoints of the center line and we retrace it in between those endpoints by using what is called the cost function. Essentially what this does is that it minimizes cost, which means it's going to penalize the center line from passing through the floodplain, for example, for passing through locations that don't have high flow accumulation, which is the area that you see here, and high curvature that you see here. So we're essentially integrating. There's more complex cost functions that we use, but that's essentially the idea. You think about what makes the channel path special, what makes that path the preferred path for water, integrate those attributes into a cost function, and then detect the center line as a geodesic, a line of minimum cost that essentially takes all the points that satisfy that criteria and minimize the cost. The main advantage of this type of approach is that barriers like bridges and things like that are not a problem because the cost is minimized globally. And so that means that you don't have to do as much hydro-conditioning of your DEM because you can just go through. It's not perfect, of course. There's local inaccuracies and things like that, but for the most part, is able to deal with terrain depressions, deal with bridges and things like that without you having to modify the terrain in any way. So as same workflow, so I don't have to spend much time because the guys just presented it. Take the national water model predictions, use that net terrain information, I'll LiDAR now, though not a 10 meter, to get synthetic rating curves that essentially allow us to relate discharge and depth. So if I have a given prediction, what depth do I have? And then take a hand approach to translate that into a flood inundation map. Mark did a wonderful job explaining it. So you got what the model looks like. It's pretty easy. It's just based on terrain information. We take a Manning's approach and we take the national water model prediction. And back to what, this, I don't need to explain you. You have a good idea of where, at what height, essentially that location is going to flood. So back to what people were asking, we have a couple of papers. One was published a few years ago. One is hopefully going to publish soon, in which we compare the performance of the model with local data, FEMA maps in local rivers, as well as with the big collection of the high watermarks during Harvey. The performance is pretty good. I mean, I would say where the hand model, will be more in trouble will be, of course, if you have hydraulic structures. I mean, any detail that, the model is not going to be able to see because it just sees terrain information. So certainly when you are, in proximity of a bridge, that's not going to give you a super accurate behavior because it's ignoring the hydraulics of the bridge. And we're using a Manning's approach, which is a normal flow approach. But other than that, when you're looking at extent and depth, actually the performance is quite good. So what we've been doing now is that the hand is really height above nearest drainage. So when we integrate the national water model prediction, we are really looking at fluvial flooding. We're integrating now with Patrick and our co-advised student, Matt Praser, an approach for pluvial inundation. And so we took this approach, which you see on the left, which is the field spill merge developed by a different group. And actually that approach was developed across the resolution, but we integrated it, brought it into LiDAR, and essentially now works with GeoFlood to get a pluvial and fluvial map. So if you have the national water model prediction and a prediction of rainfall, we can get both the flooding from the river as well as the flooding from direct rainfall on the floodplain. And that's quite important because we had a whole series of events, including Harvey, where flooding was in fact predominantly pluvial. And this is an example of a 2015 flood, which was a massive event that happened in Austin around Memorial Day. And this is essentially gives you the difference locally in flooding experienced in Austin if you were to include the pluvial component versus if you just accounting for the fluvial component. So clearly there were areas to see a vast increase in flooding once you account for the fact that some of the flooding was coming directly from rainfall. So how does the social vulnerability piece come into the picture? Well, we integrate that social vulnerability map that Patrick was just showing with this information of flooding. And so we bring the social vulnerability index, the same one that Patrick explained, and couple it with this flood map. This is for a specific event. So you can think of this map as a consequences of an event, or we can do that over a variety of events. But essentially you see again here that decoupling between East Austin and the West Side, where the East part is more socially vulnerable, but we do have locations that, although they were not in the social vulnerability map, but they are in fact vulnerable to flooding in other parts of the city. So as of now, this is just an overlay of the information. So essentially it's added to the flood inundation map. We are now moving into a more dynamic approach, if you like, in starting to think about what prevents people from, for example, to reach certain services during a disaster. Now, as we were talking about collaborations at the beginning of this meeting, this has been super important. So I would say this work really, kind of bridges the more academic research side, which is where we push the methods, to really the applied side and what the stakeholders need. So we've been working a lot with the city of Austin. We've been working a lot, for example, with this group in Southeast Texas through a collaboration with Lamar University. Lots of stakeholders involved, and it's really been the exchange with the stakeholders that has led to the development of these methods, as Mark and Derek were talking about, kind of understanding what the stakeholders need. And in this case, really the emergency responders, which is the community we've been mainly working with, it is something fast. So this is an example now to conclude the talk as to how we're providing now this information flood inundation maps to the emergency responders directly. So if you talk to former firefighters or firefighters, and we are lucky that some of them actually work with us directly in the research team, they'll tell you the hardest thing is when you respond to an event to understand how bad it is, because you only have information locally, and what you don't know is how bad is it and where else do you need to be at the same time, right? And so what we're doing then is to provide this information. So imagine you have aerial imagery, then of course we have terrain information. We extract the center line, we extract the hand map. So now we have a flood inundation map. Well, this is becoming a library of flood inundation maps that are integrated into an application that is called Pin to Flood. So this was piloted before. It's now a project funded by FEMA, so through the Texas Division of Emergency Management. And so this is actually just started. So there's going to be the full development of this application, as well as the testing, of course, and implementation over the state of Texas. And so imagine that's the following. So the firefighters are going to have this application on their iPads, essentially. They can go in the field and they can say, okay, if I'm at a given location and I see flooding, I can drop a pin, right? And so right now, that's only your local information, but what you want to know is where else is it bad? And so imagine you have a bunch of firefighters that are, in fact, responding to various local flooding, and they're dropping these pins. From these pins, you can essentially extrapolate the most likely extent of the flood from the hand map. Because if I know that it's flooded at my location and I'm at a given elevation, then I can essentially extrapolate from the library of maps information of where else is likely to be flooded, because I'm seeing flooding at my location specifically. And so this is going to give them instantaneously an idea of what's the likely extent of the event. And if you like, there can even be information on which address points are going to be the most impacted. And that's get a sense back to the household scale of, where are the most people, where do you need to be, where do you need to evacuate people. Now, this is for now just the extent, and that's what Pin to Flood is going to be developed with. But you can think about depth, of course, as Derek was talking about, right? Depending on depth, the emergency responders will change the type of vehicle they will use to access a given area. But again, this brings us back to what Patrick was talking about in terms of scaling, right? It's not trivial to get some of this information at the household scale. The address point is a good representation of the estimate of risk, of flooding risk at the household scale. But some of the other information, like the social vulnerability index, is not that trivial to get information at the household scale. In fact, we are designing a survey that we're about to deploy. And again, you can't ask people where they live or to provide you the specific address. That's not information that we're going to be able to see. So there's an interesting interplay of scale here and some good work that needs to be done in understanding how to integrate all these layers to provide the best information to the emergency responders, but also to the residents and other people involved in the event. And with that, I think this is the last slide that we have. Thank you very much.